Okay, we've just carried out an experiment and we have observed how the presence of a crack can ultimately lead to failure of this structure. That was a very simple structure that we just experimented with, a tape adhered to a surface, and I was pulling on it with a band. But ultimately what we observed was that there was a critical energy that is stored in the system within the band, and ultimately when we reach that value, the crack tries to self-propagate, and it feeds its growth by extracting energy from the system, which we observed by the tip of the band moving up, and hence the total energy in the band being reduced. So where is that energy going to? Into the propagation of the crack through the generation of new surfaces. So that simple experiment will help us formulate a fracture criterion. A criterion that ultimately helps us assess whether a structure with a crack will ultimately fail or not. And let me summarize the experiment that we have just carried out in a slightly different context, but ultimately the idea is the same. What we have presently is a plate, and this is not a perfect plate, but rather it has a crack on one side. And well, let me depict the crack by an exaggeration by really putting some slit there. This crack, of course, has some surface area, let's say, that is associated with width A. Okay, so the length of the plate is, let's say, L, and what we are going to do is we are going to apply onto this plate some force, and we are going to see what happens to the plate. Well, two things might happen simultaneously or independently. Well, first, the length of the plate might increase. That's certainly something that's going to happen initially as the force increases, just like the elongation of the bend that we have seen in our simple experiment. Two, at some point the crack might propagate, so it might increase in length. So the size of the crack might change by, let's say, a incremental amount dA. Okay, all right. So let's see which one will happen and when it will happen. So the first thing I'm going to do is I'm going to monitor the total strain energy that is stored in the system due to the elastic deformation of the plate. It's not necessarily something that is easy to calculate analytically, but certainly it is something that we can calculate at least through numerical means. So, well, for this purpose, I'm going to draw the force over change in length of the plate. And well, what will happen is that I will increase the force, the plate will elongate, will increase the force, the plate will elongate, I will increase the force, the plate will elongate, etc. At any given stage, the area under this curve is, let us call it U, as we have defined it, is the total strain energy that has been stored in the system. Now, I'm going to do something that is sort of a virtual experiment, a thought experiment. I'm going to assume that we pull on this on this plate, just like I pull on the band, and at some point I imagine that the crack will propagate. Remember what happens in our simple experiment. When the crack propagates, the tape peels off, the other tip of the band will start moving up, and hence this total force in the system is being reduced. So presently, I'm not saying physically that the crack does propagate, but let's assume it does. If it propagates, what I know will certainly happen is that the net force within the structure will decrease. Okay, so what I'm assuming is that I pull on the I pull on the plate, I come to a certain point, and I fix the amount of elongation, just like I fix the amount at which I was pulling on the band when natural deadhesion peeling off was happening. I fix the position of the top surface. Let's say the bottom is fixed, if you like. And I am imagining, in this case, however, it's a virtual experiment. It's not necessarily the tape is peeling off, or in this case, the crack is propagating. I'm imagining that it does virtually. And what will happen as a result of that is that the force will decrease, right? Because the net force decreases in the elastic band as the tape was peeling off. So in this case, when the position of the top surface is fixed and this thing keeps propagating, the stiffness of the cross-section is being reduced because there is now less area carrying that load, and it will elongate more easily. Or conversely, if the elongation is fixed and the crack is propagating, because the stiffness is being reduced, the force that I measured is also being reduced. Now, when the force gets reduced as a result of the virtual propagation of the crack, the net amount of energy that has been stored in the system will also get reduced. Originally there was U, and now suppose there was a change in the crack size, which caused a increase in crack size, caused a decrease in the force, and because the tip of the plate is being fixed, the amount of elongation, what happens is that the total amount of energy that is stored in the system has been reduced from this amount to this amount. And the difference is the amount that I have shaded. Let's call that du. It's a change in the amount of energy that has been stored due to the fact that crack has been propagating. I am indicating the crack propagation with an incremental value because I assume it's a very small value, and hence the change in the strain energy is also going to be small. Now let's say the thickness of this plate is T, and what I'd like to calculate is the amount or the rate at which the strain is released. So I can easily do that by looking at the change in the energy. Okay, so that's the amount of energy, strain energy, elastic strain energy that has been removed from the system. And the amount of energy that has been removed has to do with the amount by which the crack propagates. And therefore, for a unit propagation of the crack size, this is the amount that has been released from the system, the ratio of du to dA, the amount by which it propagates. So now what I'd like to do is I'd like to relate the amount of energy change to the amount of new crack area that has been generated. dA is just the length of the crack. There is also the thickness, so the new area has to do with dA times T. So why don't I scale this amount of energy released by T as well, so that I see the amount of energy that has been stored by unit propagation, unit increase in the crack size. Now also du is negative because energy obviously is being released from the system. It's decreasing. To have some positive value, I am going to put a negative sign. So what we have here is a quantity that is certainly in units of energy per meter squared. The typical value to denote that with is kilojoules per meter squared. That's the unit of this quantity. It is greater than 0 and it has a name. It is called G. And it is, well, the symbol is G, the name is strain energy release rate. Okay. So here rate refers not to time but rather to the size of crack, how fast the crack increases in size. So that's what the rate is referring to. So derivative with respect to the increase in crack area. Okay, so what was the thought experiment? Let me summarize again. I have a structure, I pull it up to a certain point, the load reaches a certain level, and I assume that the crack propagates, not physically perhaps, but virtually, and therefore the crack size increases as it does so, the cross-sectional stiffness gets reduced and hence the load gets reduced. And because the size, the elongation, overall elongation of the plate is fixed, the total energy that has been released from the system is simply calculated by that blue shaded area, and that area, when I scale it properly, indicates the amount or the rate with which strain energy is being released from the system. So it's kilojoules per meter squared. So now, can I calculate G? Again, I can in principle. It does depend on the geometry of the system, it depends on the load, it depends on the material that I am considering. So many factors here come into play. So it depends on the geometry of the problem, on the load, and on the material that the structure is eventually made of. So, but now let's step back. What I said is I'm doing a virtual scenario. I'm assuming that the crack propagates, and the energy that is needed for the propagation of the crack, just like in the experiment with the tape and the band, is coming from the system. The crack propagates, and to propagate, remember, it generates new surfaces, and the energy that it needs comes from the system. So G is essentially the rate at which the system can supply energy into the crack propagation rate. Okay? So the rate at which the system can supply energy to the crack growth is G. Now, on the other hand, let's put a big but. We know, we've just discussed that energy is really needed to create a crack surface. Now, I know that's what I've just said, the amount of energy that the system has available to make the crack grow in rate form is G, but what we are saying here is that there is a physical energy, a certain amount of energy that is needed to create a new crack surface. And chemists have called this quantity GC. It is the so-called critical strain energy release rate. So physically, that's the name, physically it corresponds to the energy needed to create a unit area of crack surface, right? So now my question is now simple, and I will ask the question, and it's worth that you pause and think about the answer for a second. Now, what we are saying is that the crack, in order to physically propagate at any stage of loading, requires per unit area of growth GC, the critical strain energy release rate. It's a physical quantity. Physically, you have a pair of surfaces. This is a well-defined amount. Okay? All right. So, on the other hand, at any stage of loading, what the system has available to provide into the crack propagation is G. That's the energy, the rate at which the system can release energy. So the system has, in rate form, G available. The surfaces need GC to propagate. So the question is, in terms of G and GC, can I predict whether the crack can grow or not? So what you should notice is that G is something that will continuously grow, right? Because the amount of energy that is released at any stage is this area. If I had unloaded at this stage, the amount of energy that was stored would be just this green portion. If I load more and more, the amount of energy that is available when the crack propagates by a certain amount is going to be essentially larger and larger in an actual loading scenario. So G, as the load increases, will start increasing. And on the other hand, physically, what is needed is GC for the crack to propagate. So think about that question for a second. Now, it turns out that the answer is already in a form that we have formulated earlier failure criteria in terms of. We have a certain quantity that lumps many different processes that are going on. I'm loading, the thing is deforming, and there's a certain amount of energy that is being stored, and I imagine if the crack propagates, it is going to release a certain amount of energy G from the system. So that's what I have from my calculations for a given loading. On the other hand, what I have physically as a bound is GC. This is what is needed for propagation to actually occur. So if the value of G is less than GC, crack will not propagate. As soon as it is equal to GC, it's in the process of propagating. If you make a design in which you find that for a given load G is larger than GC, that means the crack will immediately propagate and fracture the system. Okay, so I will write my criterion as such as I've done earlier. Okay, so if G is less than or equal to, if it is less than GC, it will not propagate. If it's equal, it's in the process of propagating, and it can never actually physically be larger than GC, at least not in the context that we are discussing. So this is called the Griffiths criterion. For fracture. It is an energy-based criterion to highlight. Okay, we're talking about energy calculation of rates and everything. If I had asked you this question, a formulation of that criteria based on these discussions, you certainly would have been able to answer or come up with that criterion. Well, Griffiths have unfortunately has done it earlier in the 1920s, and he has become very famous for it. So now we are understanding really quantitatively what is happening in the simple peeling of experiment that we did. And we have observed indeed that there was a critical point reached when G is equal to GC in my experiment, when the tape started to peel off and the energy that was being released from the system was always sufficient to keep the tape peeling off, the crack propagating towards ultimate failure. And what you can also recall at this point is eventually when G is equal to GC, in our experiments, the physics was a little bit different. The process was rather slow at the beginning, but ultimately remember that the failure is catastrophic. It all of a sudden propagates and the band just peels off before the whole interface has failed. At some point, the crack propagates very rapidly and just peels the tape off, or in this case, will crack through this structure. All right. Now, the reason I said my process was a little bit different is because I have assumed that all the energy that is being released from the system is going into the creation of new surfaces. So there's a certain energy that is required to create the surfaces, and the system releases some amount G, and I'm setting G equals GC, and that's when failure occurs. So what I'm saying is all the energy that is released from the system is going into the creation of the surfaces. But in reality, perhaps in my experiment, the tape was deforming plastically, or perhaps in this case, this is a metal, there's significant plastic deformation. Plastic deformations also require work, and hence, in this criterion, in this energy-based criterion by Griffiths, what we are also saying is that there is little or no plasticity effect, or for that matter, any energy that is going to anything else other than the creation of cracked surfaces. So this is a perfect discussion that is suitable for brittle fracture. Brittle, again, referring to the fact that there is little or no plastic deformation. Okay, So, okay, great. Well, now what we have so far is a formulation that is, or a physical explanation of when cracks grow. Now, the problem is the calculation of G. It is quite hard, actually, even for simple geometries such as that. And that is where a seminal contribution by another person called Irwin comes in. And let's put that to a side. Now, Griffiths did explain the physics of fracture, but the process of working with G, and for that matter GC, is not that simple. So engineering-wise, it is preferable to have a simpler approach, and such an approach was proposed in 1950s by Irwin, and he rewrote Griffith's criterion in terms of K1. So I'm saying K1 because the experiment that we just did had to do with a plate with a crack, and when I pull on the crack, the surfaces of the crack move apart from each other, just like in the peeling off of the tape. So that's an opening mode, which is K1. So what Irwin did was, first of all, he said that, well, there is a relation between the critical strain energy release rate and a critical amount to which the stress intensity factor must reach. So here I am just like putting a critical symbol C on G, I'm also putting a critical symbol on K1. And the relation physically is equal to square root E prime. So not the Young's modulus, but very close to the Young's modulus. I'll make a note of it very soon. And so you can take G and multiply it with E, take the square root, and boom, you have a value, the so-called critical strain energy, the critical stress intensity factor. All right. Now, we don't have to remember this relation between the critical stress intensity factor and the critical strain energy release rate, GC, but we do have to remember what this name stands for, is K1C, and we also need to remember that this quantity has an alternative name that you will come across just as often, if not more, and it is called the fracture toughness. Remember, toughness has to do with the amount of energy that has been stored in the system physically in a tensile stress test. So here, in some sense, it's also related to energy. So fracture toughness is another name for K1C. So notice that it is a quantity that will eventually depend only on the material property, because GC is a material property, but also a little bit on the stress state. And the reason it depends formally on the stress state is because E prime is a quantity that actually depends on the stress state. If it is a state of plane stress, then E prime is equal to simply E. If it is a state of plane strain, it's equal to E over 1 minus nu squared, where nu is the Poisson ratio. Now, the difference between E and E over 1 minus nu squared is not huge, and therefore you can think of K1C almost as a material property. It is certainly the dominant contribution to the value of K1C compared to the stress state, because this factor is very close to unity. But for that reason, and sometimes for that reason exactly, K1C is referred to as a purely material parameter, but keep in mind, in reality, it's a function of both. So now, what Irwin said is, well, would you like to predict whether or not fracture occurs? Very simple. You give me the structure, and for that structure, eventually I will be able to calculate the stress intensity factor. It is K1. Let's say we have a plate, and there is a crack of width 2A in a plate of width 2B, and we are pulling on this plate with a certain far field load. I know exactly what K1 is at any stage of loading. So I know the value of A and I know the value of S. I can calculate K1, and I keep increasing S. As I keep increasing S, the value of K1 will keep increasing. But there is a certain critical value of K1, it turns out, that is needed for this crack to propagate catastrophically and break the structure apart. Until K1 reaches that value, we don't get fracture. And what is that critical value? It's exactly this. It's something that we can measure directly experimentally, or if GC is available, we could perhaps use the value of GC. But now, the fracture criterion of Irwin is the following. Okay, and this is what we are going to refer to as our brittle fracture criterion. And the beauty of this criterion is that K1C, it's available, it's tabulated just like the yield strength or the ultimate strength or whatever of materials. K1C is also tabulated. In fact, in one of our experiments, you're going to determine what K1C is for a certain type of material. And K1 is something that is easily calculated from the physics mechanics of the problem. You give me the value of the load. If it's sufficiently large, K1, in other words, if it's equal to K1C, fracture will occur. Otherwise, if it's less, fracture will not occur. And hence, I can easily determine whether or not crack propagation towards catastrophic failure is going to occur. Okay, so that is our brittle fracture criterion that we need to know by heart, just like we need to know the expression of K1. This, I should note at this stage, is a simplified expression for the stress intensity factor. We're going to build up upon that. Okay, now having said all of this, let us demonstrate what we have with a simple experiment. What we are saying is, first, the presence of the cracks is very important in a structure. So what I have here is a specimen that you are going to actually use in the experiment that I have just mentioned in the lab. And we have put a crack in it of a certain size, and we're going to load the structure. I can certainly pull on it, and that will try to open this crack, but the load I have to apply would be a lot. I can try to open this crack in a different way by bending it in that direction. So I'm going to bend it like this, and I will try to open this crack. Now remember, earlier we said that mode 2 somehow is a type of loading that is naturally induced by bending, but mode 2 had to do with sliding of the surfaces. What you have to keep in mind at this stage is bending does not necessarily always make the surfaces slide with respect to each other. In this case, when I bend in that direction, I'm going to actually try to open the surfaces of the crack. I'm going to try to move them like this. So that's the opening mode, and hence mode 1 loading. Right? Similarly, the fact that surfaces slide with respect to each other doesn't necessarily, again, have to be induced by bending. Actually, it turns out that shear forces that are more natural to torque type loading can actually also induce mode 2, in other words, sliding type failure fracture. So we're going to discuss those more. But presently, I have an opening mode that is going to be induced by bending. So what we are going to say is that the presence of the crack reduces the strength of the structure. Well, how does it do so? Well, first I bend in this direction, and what I'm trying to do is I am bending like this, and the crack is certainly there, and actually the force that I'm applying is quite large, but nothing is happening. Well, why is nothing happening? Because there is a solid cross-section here, and that's the effective cross-section of the beam. And when I'm trying to bend, I'm trying to reach That's where the maximum tensile stress occurs, and this is a brittle material, it turns out. I'm trying to reach the ultimate strength of the material, and the ultimate strength is actually quite high, and I cannot reach that value, and hence I cannot break the specimen. So when the specimen is not breaking, and that's because I cannot reach the ultimate strength. So fracture, the way we are discussing it, is not really reaching, it doesn't have to do with reaching the ultimate strength. It's an entirely different process, and to demonstrate that, now I'm going to flip the specimen over and I'm going to try to again bend it in this fashion. Here I applied a huge amount of force. You can perhaps even see the specimen bending a little bit and nothing happens. But in this case, what I'm going to do is I'm going to load the structure, and there is a crack. At the tip of the crack there are huge stresses. If the crack were to propagate at any stage of loading, it would release a certain amount of energy from the system. If that energy is sufficient for self-propagation of the crack, it will propagate on its own catastrophically, very rapidly, and all the process governed by pure, simple elasticity combined with the physics of generation of new surfaces. And that's what we're going to observe now. I'm going to apply a load. So the load, believe me, it's not large at all. You could do this experiment with your hands as well. And I reach a certain value, and easily the specimen just breaks apart. Okay? And when you look at the surfaces of the specimen, perhaps it's not very cleanly visible in this case, but what you would eventually or could eventually observe, and you can do so in the experiment, the surfaces are very shiny, and that means that physically what's happening is that the bonds within the material is being ruptured, and notice that initially there was no interface. It was one solid material, but there is still an interface because the material is naturally bonded to one another. The internal structure of the material is continuous. So I'm breaking the bonds within the material, and that breakage is catastrophic, and all of a sudden I could break this material with little force. And I did so because K1 reached the intense critical value, which is the fracture toughness. Okay, so we have the basics at hand. Next, we're going to immediately demonstrate those ideas with a simple example.